Hi, my name's Tony Preston, and in this short video we're going to run through some of the basic functionality of Agilent's N9340B handheld spectrum analyzer. If you want to learn more about the N9340B, make sure you get a copy of the complete user training and application tutorial DVD, which you can obtain free of charge from Agilent Technologies. Just go to the URL shown at the bottom of the screen. It runs for about an hour and provides far more detailed training on a whole range of practical topics, such as making interference measurements, measuring the modulation characteristics of carriers, sweeping antennas and diplexers. And if you've not done so already, you might want to download the PDF of the Agilent N9340B demonstration guide so that you can follow along during the course of this presentation. Let's start with a quick overview of the instrument's front panel. Here, below the display, is the instrument's power button. Just press that to toggle the instrument on and off. And to the right of that are a range of function buttons. Here you can set things like the frequency range, the frequency span, the amplitude range and reference level and attenuation, the resolution bandwidth and sweep time of the instrument. You can turn on additional traces. You can make sophisticated measurements by pressing the measure key, such as occupied bandwidth. You can press the mode button in order to access different modes of the instrument, and the sys button for changing settings such as the date and time or seeing which options are installed in the instrument. There are the usual three methods for data entry, either using the numeric keypad, the up-down arrow keys, or by turning the knob. You can press the marker button to turn on a marker and access various marker functions. And of course, we've got the soft keys, the meaning of which changes depending on which of the function keys I've pressed. And probably the most useful button on the entire instrument is the green preset button. Pressing this resets the instrument and puts it back to its factory default state. It's highly recommended that you always press that green button before starting a new measurement to make sure that any strange settings that a previous user may have set up within the instrument have been cleared. On top here, you can see there's a built-in loudspeaker for listening to demodulated audio, and below that is a light sensor. The N9340B has an incredibly bright daylight viewable display that, if using indoors or in dark conditions, could actually be too bright. So with the automatic light sensor activated, the instrument will automatically adjust the screen brightness depending on ambient light conditions. If I press the sys button, you can see here there's a button called brightness. If I press that, you can see it's set to manual and level of 5. I can turn the knob and make the screen brighter or dimmer. If I press the button again, it changes the brightness setting to auto. Now the light sensor is active and the screen brightness will be automatically adjusted depending on the ambient lighting conditions. I'll set that back to manual for now. There's another useful function if you're working at night or in a dark communications room. The key backlight button, if I press that, I can turn the brightness of the key backlights on. So I press brightness and let's set it to high. Now if we dim the studio lights, you can see that all of the buttons are now backlit and easily viewable in dark conditions. Before we start making any measurements, let's see how we can save and recall measurement setups and results. Everyone these days needs to keep a record of their measurement results for documenting in a report or emailing to a client. The N9340B makes this especially easy, as you can store trace data, screen captures, limit masks, spectrum masks, and even instrument setups to either the internal memory or directly to a USB memory stick. Saving the entire instrument setup is incredibly useful, as it means you can share the same setup between multiple instruments, ensuring that every measurement is made the same way every time, regardless of the operator. Here I've set up the instrument to monitor the output from a mobile phone base station. So let's save the setup into the N9340B's internal memory so we can quickly recall it in the future. And if you're following along in the demonstration guide, then turn to section 2 and we're going to follow the instructions at the bottom of the page there. So let's call up the File Save menu by pressing the sys button, and then we're going to select the internal memory. So I'm going to press File and then File Setup, And the save path is currently set to local, which is what I want. But if I wanted to store to the USB memory stick, I could change that to USB. But we'll leave that as local for now. Then we're going to select the file type. So we press File Setup, and the kind of file we want to save here is an instrument state, so that I can recall it later if I wish to. So I'll press the State button. Then we can enter a file name using the numeric keypad. So I'll call this 123. And then I'll press Save, and that state has now been saved into the internal memory. And you can see that here, the file name is 123, it's a state file, and it was saved on the 1st of October 2010. Now let's do exactly the same thing again, but this time save the instrument setup to the USB memory stick. So I'll press File Setup, and change the save path to USB. I can now give it a new file name, I'll call it 456, and I'll press Save. Now the reason you can't see that file saved on this display here is because the path for the display is still set to local. So let's view the USB stick. And here you can see on the USB stick, it says the path is USB, and we have a file called 456. It's a state saved again on the 1st of October 2010. Now let's say we've gone out on site and we want to recall that setup. Let me first of all preset the instrument to put it back to its factory default state. Then what I'll do is I'll press the Sys button and then File, and if I change the view to the USB memory stick, you can see here our setup saved as 456. If I now press Load Now, you can see immediately the whole instrument has been reconfigured to exactly the same setup that I had for the previous measurement of this base station. Let's start by making some simple measurements of a 100 MHz RF carrier, which is being generated by one of these fantastic new MXG signal generators from Agilent Technologies. I've set the signal generator frequency to 100 MHz, the output level to -10 dBm, and turned the RF on, and let's connect the signal to the N9340B analyzer. So I'll disconnect the antenna, and let's connect the signal to the analyzer. And I'm going to press the green preset button, and following the instructions in the demonstration guide, it says press frequency 100 MHz. There's the signal. It then says press span 10 MHz. That's to zoom in on it. And now we can press the amplitude button and rotate the knob to bring the signal to the top of the screen. Fantastic. So there's the 100 MHz signal. Now if I want to measure that, I can always press the marker button, and we can see there that the marker is indeed at 100 MHz, and the level being measured is -10.8 dBm. Now, if you turn to section 6 of the demonstration guide, you'll see one of the most fundamental applications of a spectrum analyzer, searching for and measuring low-level signals. Examples might include looking for weak 2.4 GHz Wi-Fi signals out in the field, or searching for interfering signals, surveillance applications, or, as in this demonstration, we're going to be looking for the third harmonic of a transmitter. A spectrum analyzer sensitivity, its ability to measure very small signals, is a key specification of any spectrum analyzer. With the optional preamplifier that's built into the N9340B, you can measure signals as low as -144 dBm, provided you know how to set it up properly. So with the 100 MHz signal from the signal generator still connected to the analyzer, let's press the preset button, and then we press frequency 300 MHz and a span of 150 kHz. And you can't see this third harmonic signal on the screen, so let's take a few steps to improve the sensitivity of this measurement. Firstly, I'm going to press the amplitude button and adjust the reference level to bring the trace further up onto the screen. And we can just about see a glimmer of a third harmonic signal in the middle of the screen there. Now let's reduce the resolution bandwidth. that will have the effect of reducing the noise floor. If you don't understand why that's the case, take a look at application note 150, which you can download from Agilent's website, and that explains all about resolution bandwidth and Boltzmann's law. So anyway, I've pressed the system bandwidth button, and I'm going to reduce the resolution bandwidth down to 100 Hertz. And you'll see now the noise floor immediately drops, and we can see the signal, the third harmonic signal from this signal generator, much more clearly on the display. Now there's one more thing we can do to improve the sensitivity still further, and that's to remove all the attenuation in the input signal path. So I'll press the amplitude button, press the attenuation button, and enter 0 dB. And as you can see, that's given us roughly another 10 dB of sensitivity on the noise floor. And we can clearly see now the third harmonic signal from this signal generator. And if you want to measure the level of that, let's just press the marker button and we can read it off here, minus 81 dBm. With the RF spectrum becoming ever more crowded, the ability to see transmitters turning on and off over time is a very useful function, both for interference analysis at base stations and for surveillance by the military and security forces. Turn to section 8 in the demo guide and you'll see how we can use the spectrogram capability of the N9340B to identify and measure signals across a wide spectrum over a period of time. Now, to demonstrate the spectrogram feature effectively, the frequency range that you select is going to depend very much on where you are located in the world. But for this application here, I'm going to look in the 400 MHz band. So I'll press the instrument preset button, and then I'm going to set the frequency to 425 MHz, and I'm going to set a span of 50 MHz. Now, to improve the sensitivity, I'm going to change the reference level to minus 75 dBm. I'm going to turn the preamplifier on, and I'm going to change the scale per division to 5 dB per division. And you can now see a range of signals on the screen and a couple of intermittent ones. Now, to turn on spectrogram, we just press the measure button and then press spectrogram. And what's happening now is that we still have the frequency spectrum on the x-axis of the display with a center frequency of 425 MHz and a span of 50 MHz. But on the y-axis, instead of showing amplitude, we now have time. Amplitude is in fact displayed by the color of the trace. So green is a weak signal and red is a strong signal. You can see already that we have a number of continuous transmitters shown on the display, and these red dashed lines show transmitters that are turning on and off. Now, I can change the update interval for the spectrogram measurement by pressing the update interval button. Now, let's say I only want to capture a trace every 10 seconds. I can type in 10 seconds, and now each new sweep will be performed after a 10-second delay and added to the collection of traces that make up the spectrogram. Let me set the update interval back to off so the trace will now update as fast as it can. Now, a useful feature again on the spectrogram measurement, if we want to know at what frequency these signals are, I can turn on a marker. In fact, there are two markers we can turn on. I'll turn on marker 1 and I'll turn on marker 2. And if I press the frequency button here and turn the knob, you can see the two markers here shown as black and white crosses will move across the display. So I'm adjusting marker 2, which is the white cross there, and that's showing me that that signal is at 411.195652 megahertz. You can also see the values of frequency for both markers, marker 1 and marker 2, and their amplitude levels at the top of the display. What's even more useful though is at the bottom of the display here, it shows the time values of the two markers. So if I press the time button and adjust that, you can see that the white marker is now showing me the amplitude values at a previous time during the recording of the spectrogram traces. Now, if I want to save one of those specific spectrogram traces, I can set the display mode to trace, this shows me one of those historical traces that is being used to create that spectrogram diagram, and we can now save that trace into the internal memory or onto the USB memory stick. In the previous sections, we've been making measurements of RF signals. In other words, the output from transmitters. There's another really important use for handheld spectrum analyzers when out in the field, and that's the ability to measure RF devices, such as filters, diplexers, cables, and antennas. Because these devices don't generate a signal themselves, we need to connect a test signal to the input of the device and use the analyzer to measure what effect the device has on that signal. The tracking generator option in the N9340B does exactly this. We connect the tracking generator output to the input of the device under test, and the output of the device to the analyzer's input. The tracking generator produces a signal that sweeps across the same frequency range as the analyzer and plots the device's frequency response on the display. This measurement is sometimes referred to as frequency response, transfer function, insertion loss, or S21. All these are just different terms describing basically the same measurement. So what I have with me here is an RF diplexer or duplexer, which is a filter that's commonly used in base stations for separating the receive signal from the transmit signal. Now this is actually two filters, so if you're going to use one of these as the device to measure, be sure you terminate the third port with the 50 ohm load as I've done here. So we have the tracking generator signal coming out of the N9340B into one port of the filter, and then the modified signal coming from the filter back into the spectrum analyzer. Now you can follow along in section 9 of the demonstration guide. Bear in mind your filter won't be exactly the same as mine, so the frequencies of course will be different. So we'll start by pressing the green preset button to reset the analyzer, and I'm going to enter a center frequency of 430 megahertz and a span of 50 megahertz. Now let's turn the tracking generator on, and to do that all we have to do is press mode and scroll down to select tracking generator and then press enter, and we'll turn the amplitude of the generator on, and you can immediately see a plot of the frequency response of this filter. There's a couple of things I'm going to do to improve the dynamic range of that measurement. I know that this filter has about a 70 dB rejection around these frequencies here, so I'm going to increase the amplitude of the tracking generator up to its maximum, which is 0 dBm, and you can see that we've now got a far broader dynamic range. Another thing I can do, as with spectrum analysis, if I want to increase the sensitivity even further, I can press the bandwidth button and narrow the resolution bandwidth down. I'll just show you. Let's reduce it down to 30 kilohertz, and you can see the noise has now disappeared from the bottom of the notch of that filter, but the sweep time has of course slowed down. So it's usually a matter of choosing the best compromise between faster sweep speed or better sensitivity. I'll put this back to automatic. Now, as you know, when making network analysis measurements, even simple ones such as this for the insertion loss of this filter, we are actually making a relative measurement, not an absolute measurement. So in other words, we're comparing the frequency response of this filter with a known standard device. Now in this instance, I'm going to use this N-type through, and I'm going to assume that this is perfect zero insertion loss. Now this is a good place to point out that you should always make sure when doing network analysis measurements that you have really good quality connectors and adapters and cables. So we're going to be assuming that this device is a perfect device and making a relative measurement of our filter with this. So now I've got the spectrum analyzer set up the way I want it for this measurement. I'm going to disconnect the filter. I'm going to replace the filter with my through. And if you're following along in the demonstration guide, it now says press mesh and then normalize and then store reference. That's trace 1 into trace 4. So press store ref and then turn normalize on. And you'll see that the yellow trace on the display here has now normalized itself. Previously it was a little bit down on the display here, and now it's 0 dB right the way across the top. So we now have a calibrated or normalized reference plane here. So I can now disconnect the through and reconnect the filter, and we're now making a calibrated measurement on the display. And of course I can press the marker button and I can turn on up to 6 markers. I can measure the frequency of the notch filter, I can turn on marker 2, and I can measure, say, the insertion loss in the passband up here. Now, another measurement that you'll frequently find you need to make out in the field, besides measuring the frequency response of a diplexer to check that it's tuned up properly for the transmitter or for making adjustments to it, would be to measure the return loss of a device, either of a diplexer or perhaps more commonly an antenna. To do that, we're going to need a directional bridge, and here I've got an Agilent 86205A directional bridge, but any good quality bridge will suffice. And what the bridge does is separates the reflected signal from the through signal, so we can measure the reflected or return loss of the device. Now, I've already got my instrument set up for the correct frequency range, tracking generator is turned on, so all I have to do is disconnect the filter. I've connected my directional bridge to the analyzer. I've got the source from the tracking generator coming into this connector here, and the received reflected signal from the device is coming back into the analyzer. This third port here is where we're going to connect the device. In this instance, we're going to measure the return loss of this diplexer filter, but of course we could measure an antenna or any other RF 50 ohm device. So the first thing we're going to want to do is normalize it again. So I'm connecting a short circuit because that gives a perfect 100% reflection. And then to do the normalization, I press the mesh button and normalize store ref 1 to 4, normalize on. And again, you can see the trace, just like doing the insertion loss, the trace is now normalized at the top of the display. So I can now disconnect my short circuit and connect my filter or antenna. And here on the display we can see the return loss in dB of this filter. And of course we might want to zoom in a bit, so I can press the amplitude button, scale per division, and let's set it to 5 dB per division. You can see the 2 markers are still there on the screen. I can put on another one, and we can make the measurements of the return loss of our filter. For further information on the Agilent N9340B, just go to the website shown below. You can download datasheets, manuals, a copy of the demonstration guide, and even request a free copy of the user training and applications tutorial DVD I mentioned earlier.